This is problem 1 from chapter 18. At a given instant, the body of mass m has an angular velocity omega, and its mass center has a velocity of v sub g. Show that its kinetic energy can be represented by 1/2 times the moment of inertia times the angular velocity squared, where this moment of inertia is the moment of inertia of the body, determined about the instantaneous axis of zero velocity, located at a distance of r, which is measured 2 point g from the instantaneous center as shown. Okay, so this is what we want to show, and we're going to start with equation 18.6, which says that T is equal to 1/2 times the mass times the velocity of the mass center squared plus 1/2 times the moment of inertia about the mass center times the angular velocity squared. And then they told me that I want to express this in terms of the moment of inertia about the instantaneous center. And so I'm going to use the parallel axis theorem, which is equation 17.4, to write the moment of inertia about the instantaneous center. That's equal to the moment of inertia about point G plus m times the distance squared between the mass center and the instantaneous center. Well, that they show me here. That is r, which goes 2g from the instantaneous center. Okay, so now I'm going to go back to, this was equation 18.6, and if I solve this for the moment of inertia about g, I get the moment of inertia about the instantaneous center minus the mass times r squared. Then I can take this and put it in here, and I get T is equal to 1/2 the mass times the velocity of the mass center squared plus 1/2 times, now this is equal to the moment of inertia about the instantaneous center minus mr squared times omega squared. Then I'm going to distribute the 1/2 and the omega squared. So this is 1/2 times m times v squared plus 1/2 Okay, but recall that the velocity of point G, which is shown here, since this is the instantaneous center, that is equal to this r going 2g from the instantaneous center times omega. So we learned this back when we talked about the instantaneous center of zero velocity. So if I take this and solve it for omega, and then put that in here, then I get T is equal to 1/2 m v squared plus 1/2 times the moment of inertia times omega squared minus 1/2 times m. And then I have an r squared here, but I'm going to have an r squared here in the denominator, so those will cancel out. And then this cancels with this, and you get T is equal to 1/2 moment of inertia about instantaneous center times angular velocity squared, which is exactly what I was supposed to show.